Oh gosh, so we're filming right now?
We're filming right now.
Okay, just leave it, just get it lined up. We'll go with it. Sorry for that, that's an auspicious start here. We've got this thing on a chair, kind of in this room. We're in the physics building this time. Hopefully, can they see the boards, both boards?
Yeah, but you have that up.
That's fine, yeah, that's not a problem. As long as we can see both boards, we're good. Okay, all right, guys. I want to apologize for the 1000th time, but I want you to know that we are going to be heading back, picking up our daughter tomorrow, and we're going to be heading back tomorrow, driving most of the day. But so I will be in class on Wednesday. I'll be in class on Wednesday. I don't know if I'll have your quizzes graded. It's probably unlikely, but I'll try, because I'll get back around midnight. Okay, test two. I know we talked about this a lot. I just want to, everything that I've said, I'm not going to add too much more to what I've said. But I did want to mention one other type of problem that I like. I've assigned it for textbook homework, something like it, but I just want to work an example because I really like these kinds of problems. An example would be something like what we have here. We've got this function h of x, okay, and it's equal to x squared, so it's clearly a function of x, times f of x over g of x. But they don't give you any other information about f of x or g of x. The only thing that we're told, we're just given just the tiniest pieces of information. We're told that when x is 2, f is 1 in the range, and when x is 2, g is 3 in the range, and we're also given information about the derivative at 2. We're told f prime of 2 is 0, which will help us, trust me, and g prime of 2 is 4. And then they ask us, what is h prime of 2? And at first you're like, well, Dr. Warren, you're not giving us any functions. You're not giving us anything to take a derivative of. I can't even use a flashcard for this. It's okay. We can still use our flashcards and just use these little pieces of the puzzle because this is also at 2. So I just want to work this example for you. If I'm looking at this and I want to take the derivative of this, the first thing I notice is that it's a function divided by a function. Okay, so Christian, what rule would I start? Now, Christian, I know you know this, so and you said quotient rule, so that's exactly right. But my numerator is the x squared over f of x, so I'm going to do this just in 2 steps. Now, I wouldn't expect you guys to have to do this on the test like this. This is just for your notes. So it's going to be the derivative of the top, and right now I'm just going to write it as the derivative of the top times the bottom minus the top, which is just x squared times f of x, times the derivative of the bottom, all over the bottom, what? Did you say squared? That's exactly right. Now notice I'm not done because I still need to take the derivative of the x squared times f of x. Now, Michael, what rule am I going to use if I'm going to take the derivative of x squared times f of x? And that's right, product rule. And so I'm going to do that down here. So it's going to be the derivative of x squared. Now remember, it's going to get multiplied times the gx, so I'm going to keep these parentheses. 2x times f of x plus x squared, the derivative, the first times the derivative of the second, times f prime of x. And notice I can't do any better than f prime of x because I'm not given f of x. This is times g of x minus x squared f of x times g prime of x all over g of x squared. Now, I want h prime at what value? And you can see here at 2. So now wherever I see an x down in here, I'm just going to put a 2. Now, I know this isn't exciting, but wherever I'm going to see an x, all I'm going to do is put a 2. So I'll put a 2 here, and then every other location. And so when I do that, just substituting a 2 in, you see that I would get 2 times 2, f of 2, plus x squared f prime of, 2 squared, f prime of 2, all of that times g of 2 minus 2 squared f of 2 g prime of 2 all over g of 2 squared. Now I know this isn't exciting, but it's not hard. Calculus, this kind of calculus is not hard. Now we just use our piece of information that they gave us. We were told that f of 2 is 1, so now wherever I see the f of 2, I'm going to put a 1. G of 2 is 3, so wherever I see the g of 2, like in this location, I'm going to put a 3. F prime of 2 is 0, that'll help us out, and g prime of 2 is 4. So I'm also going to do a little bit of sweeping. So let's take out our algebra broom here. 2 times 2 is 4. F of 2 is 1, so we're right here. 2 squared is 4. Didn't really matter. F prime of 2 is 0. G of 2 is 3. That's just the 4. F of 2 is 1. G of 2 is 3. So I'm looking at G prime of 2. G prime of 2 is 4. Then all over 3 squared, since G of 2 is 3. And I'm trusting you guys can do the rest of this arithmetic better than I can. But that's the basic thing. These problems are not hard, but I really like these. Now I wouldn't be telling you that, okay, if I wasn't away from you, okay? We have a test coming up, okay, and I just said I really like these kinds of problems. Okay, and that's probably about the last thing I'm going to say regarding the test on Friday. I'll answer some questions on Wednesday. I'm going to be on the road tomorrow, so I'm not going to be able to have Zoom class. Sorry about that, but I think we got a lot of stuff at least laid out today, and we're going to. So I'm not really sure what we get, and you're going to have this lecture as far as you being in class. Okay, so that's the only thing that could be on the test. Everything else that I'm going to talk about today is not on the test. That does not mean turn off the video. Okay, you're still watch the video. And so the first task I have for you is not a pleasant task. You're going to be a scribe, okay? So your job is to scribe. And let me show you what I want you to scribe. I'm kind of leaving off, starting with where I left off, really lamely in that last video. I was starting by defining what it means to be a local max or a local min. And here I've just laid it out. And so what I want you to do is I want you to pause this video, and then what I want you to do is to scribe. Okay, so scribe this definition here. Okay, and you can kind of write it down. I just want to give you a hint. You're going to write it down twice. I got lazy. I didn't. You're going to write it down twice. Everything gets written down. The only thing that will change are these things that I put in underneath. So like this says definition f of c. So you're going to say definition f of d is instead of local min, you're going to say local max. This stays the same. Here, everything after stays the same, and you're doing the same thing. With both of these. You already have the mean value theorem. Dr. Thelwell and Dr. Van White gave you that. So, but if you want to write it down again, it certainly can't hurt. And again, this will not be on the second test. So I will get out of the way. I'll get out of the way. Give you a nice clean shot. Pause that video and copy that down. And really copy it down. Okay, don't just pretend to copy it down, because as you write it down, it writes it on your brain. So copy that down. Okay, now I'm pretending like you've taken 5 minutes and actually written that down, kind of like a baker on a television show goes to the oven after stirring something up, and magically the cake's cooked. So now let's talk about these. what does it mean for something to be a local min? Okay, so I'm just gonna read the definition, and just to make sure in case things are blurry. Definition, f of c is a local min. So the first thing that we notice is that a local min is a range value. Typically, it's going to be on the y-axis if that's what we're thinking about. Okay, it's occurring at c, but the local min is f of c. Okay, definition: f of c is a local min of a function f on a domain D, or laziness, if and only if there exists an epsilon greater than 0. Don't let the epsilon scare you. It's not near as scary as it was on our first test. There exists an epsilon greater than 0 such that f of c is less than or equal to f of x, and this is the kicker, for every x in the interval c minus epsilon to c plus epsilon. Okay, so that's the definition, and we'll talk about it in a moment, explaining, unpacking it a little bit. But the definition of what it means to be a local min, f of c is a local min of a function f on a domain D, if and only if there exists an epsilon greater than 0, such that f of c is less than or equal to f of x for every x in the interval c minus epsilon to c plus epsilon. And your local max of a function on a domain D, it's the same thing. If there exists an epsilon such that you're the biggest guy for everybody in the interval. This guy's the lowest guy for everybody in the interval, but this guy's the biggest guy for everybody in an interval. Okay, so that's the definition. Like I said, we'll unpackage that in just a moment. Definition: what does it mean to be increasing on a domain? Well, a function f is increasing on a domain D if and only if, and this is a key part, for every, you should probably underline that, because that's a key, for every x1 and x2 that are elements of the domain, and this is again important, such that x1's less than x2, then it logically follows that f of x1's less than or equal to f of x2. And again, we'll unpackage this with a graph here in just a moment. Definition for a function to be decreasing. A function f is decreasing on a domain D, if and only if for every x1 and x2 in D, and this is, you might expect these to switch, but they don't, such that x1's less than x2, that remains the same, implies f of x2 is less than or equal to f of x1. So the only difference in this one is right here on this side of the implies. The mean value theorem, okay? Now listen to me. It is the nice value theorem. I can't think of a nicer value theorem than the mean value theorem, okay? So we're going to call it the nice value theorem because the word mean is more for average. The mean value theorem, if f is continuous on the closed interval AB, and guys, when I was a freshman, I just did not understand this at all. I didn't understand the importance of it being a closed interval. I'm like, why do we have this damn closed interval, open interval stuff? You know, why do we have differentiability and continuity? It didn't make much sense to me. I didn't realize really until advanced calculus, well, how important this closed interval stuff is. So it's really important that it's a closed interval. If f is continuous on a closed interval AB, and differentiable on the open interval AB, we may not know what actually goes on at A, the endpoints A and B, as far as differentiability. Then there exists a C that's an element of the open interval AB, such that f prime of C is equal to f of B minus f of A over B minus A. Okay, so again, these are the things that we're going to be spending a good part of our lecture on today to talk about. So I just wanted to make sure you had them all written down. Okay, so now pause the video, go to the bathroom, and go get yourself a drink of water, and only water. Okay, and then come on back. Okay, so let's first of all talk about what it means to be a local max and local min. Okay, we have the definitions here. F of c is a local min of a function if and only if there exists an epsilon such that f of c is less than or equal to f of x for every x in the interval c minus epsilon to c plus epsilon. Okay, guys, so let me just tell you a story, okay? When I was in elementary school, I don't know if you guys remember in elementary school, at recess, we would race, okay? And we would decide who's the fastest person. I don't quite know how these games started, but we would race and try to figure out who was the fastest person. And there was one kid by the name of Chuck Treisler that was by far the fastest kid at Montgomery Elementary, and we called him Mercury. He beat everybody by like 5 or 6 yards. Okay, and so Chuck Treisler was the fastest kid at Montgomery Elementary. Okay, and then we went to the junior high school where all the elementary schools came together, and we were in gym class, and then they were having a race. And all the kids from Montgomery were there, and we're like, okay, Chuck's going to show everybody up. And they just took off, and Chuck got beat. All the kids from Montgomery Elementary could not believe it, but Larry Coombs beat Chuck Treisler. And we were just in shock that that was even possible. But in the end, Larry was faster. I mean, they both ran track, but Larry was faster than Chuck. Then we went to high school, and there was a kid by the name of Tommy Marquette, and Tommy Marquette ended up being faster than Larry Coombs and Chuck Treisler. And Larry Marquette went to go play basketball for Ohio State after that. But while Tom Marquette was at Ohio State had 4 of the fastest sprinters in the world there at the same time. And so my point is that, we talked about what it meant to be the global max, or the biggest person. That's like the Usain Bolt, okay? You're the fastest guy literally in the world, okay? But there's these local maxes or mins. There's these little schools where you're the max or the min. Now I was never any of the maxes. I always felt like the global min in every single sporting event. But I've got a little drawing here, okay? So if I look here, and I'll point out where some of the local maxes and mins are. We can see here at C1, as I come up, let me scoot this over. I think maybe I missed a point here. We'll call this C1, and we'll call this value. Sorry, guys, I got a little careless. We'll call this C0. So this value is underneath this guy. Here's C2, here's C3, here's C4. Okay, so if I look at C0, I come up and go over. Now, guys, remember, that would be what? We didn't know this day 1 coming in, but that would be what? If this is C0, then this would be what, Aiden? What did you say? F of C0? Very good. Now there's, if you hit, F of C0 is in fact a local max. Now let me show you why it's a local max. There's going to be an epsilon so that every x in the interval d minus epsilon to d plus epsilon, the range value f of x will be less than or equal to Chuck Treisler. So this is like my Chuck Treisler. Okay. So now let's see here. If I pick an interval like this, if I choose this to be epsilon, then this would be like C0 minus epsilon. I'm sorry, I know this is not the greatest board to work on. This would be C0 plus epsilon. And now I should say, Elena, come on up here. Okay, come on up here. No, Lindsay, come on up here. Now if we just pick an arbitrary x, okay, so we blindly just pick any x in that interval. So I'm going to pretend like you picked that one, Lindsay. Okay, so now this is x. Now notice I come up and I go over, and we can see that the range value, f of x, is less than or equal to f of C0. And in fact, I don't care which x you pick in here, for every x in the interval d minus epsilon to d plus epsilon, f of x will be less than or equal to f of d. So this meets the definition of what it means to be be a local maximum. But this isn't the only local maximum that we have. We can see here that there's a few other ones. If I look here, this would also be, this point C2, f of C2 would also be a local max. Now this local max isn't as big as this local max, but we're not looking for the global max, we're looking for the local max. There's some neighborhood, and this one I can probably go as far as here. This would be like C2 minus epsilon, C2 plus epsilon, and if I pick any x in here, f of x, any x in this neighborhood, f of x is always going to be less than or equal to f of C2. So this is what we mean when we say local, okay? So we've got, there's just some neighborhood where you're the best, okay? Similarly, if you're the local min, there's some neighborhood where you're the worst. But we can see here, well, I guess I didn't draw a great picture, but there you can imagine graphs where a local min could actually be higher than some other local max. You know, we wouldn't, you know, we'd have something that maybe looks like this, comes down, swings down like this. This would be a local min, and this would be the local max. But in that case, the local min would be bigger than the local max because we're only concerned about the people in the neighborhood, the people in that school. I mean, is this making sense? Is this making sense? I don't want this to be overly complicated. But the biggest result that we're going for, let me give you a hint where we're going. There's an amazing theorem that we're going to end up proving, because math is proof, that says that a global max, and you got to imagine that's the thing we're looking for. We're looking for the Usain Bolt. Okay, we're going through hoping to find the Usain Bolt. And you can see here, if I ask you how many values are there between A and B, hopefully you're not saying there's 7. I mean, there's infinitely many values between A and B. And if I wanted to find the overall global maximum, the Usain Bolt, or the global minimum, the slowest person, the Dr. Warren, okay? If we're looking for the Dr. Warren, the slowest person, or the Usain Bolt, the fastest person in the world, there's this major theorem that's going to show us that they must occur either at an endpoint, which is kind of like what we see here. If we look over here, the biggest guy is actually the point f of b. If this is dollars, I'm getting my most money when I'm at B, okay? And f of B is the most money that I'm going to get. Everybody else in between A and B, they're going to be less than f of B. But the global max either must occur at an endpoint, so it's either A or B, or a local max, and that's why these local maxes and local mins are so important. Similarly, the lowest our stock would ever get, the Dr. Warren of the stock, okay, is going to occur either at a local min or an endpoint. So it reduces having to check millions and millions, okay, infinitely many points, to just down to a handful, your local maxes, your local mins, and your endpoints. So that's where we're heading. But not today. Okay, so that's kind of what it means when I'm talking about local maxes and local mins. Okay, so what we notice is that, even just looking at the graph, that if I'm looking at local maxes and local mins, this would be another example of what it would mean to be a local min, C4. You can see here, this would be C4, there'd be some epsilon, clearly not the same epsilon as this, C4 plus epsilon, and if I pick any x, f of x in this neighborhood is going to be greater than f of C4. But if I'm looking at this graph, a global max, a local max or local min, must occur at a place either where the derivative is 0 or the derivative does not exist. And again, I'm not proving that today. I'll justify that on Wednesday. But I'm just pointing out where we're heading. So if you're asking, well, Dr. Warren, how do I find my local maxes and local mins? You're telling me they're important. Well, you're looking for places either where the derivative is 0, which is most of them, or places like this, where we lose differentiability. So there are places, now we would also lose differentiability here. We have to check it, but it's not a local max or a local min. It's not a local max or local min. So the game works out to be this. Let's imagine that I'm trying to determine when a stock would be its highest, and I've got some time interval. The first thing you're going to do is take the first derivative, okay? Find all the places where it's 0, find all the places where it does not exist. Those are going to end up being potential local maxes and local mins. You're going to check the endpoints, your f of A and your f of B, and you're going to throw them all in the octagon, okay? And you're going to let them fight. And the guy who's ends up being the f of the biggest wins. That's your global max. The biggest loser is going to be the one that's the lowest. But math is proof, so we're a long way from actually justifying it. But that's kind of where we're heading. Okay. Let me get rid of this. You can pause the video. You can move it ahead. You don't need to watch Dr. Warren erase board. That's not real exciting. Remind me to tell you my worst moment ever as a human being when I get back. My worst moment ever as a human being. Okay, so now let's look at this definition. I also want to give some graphical justification of this. A function is increasing on a domain D if and only if for every x1 and x2 that's an element of D, such that x1 is less than x2. And let me reiterate again, this for every is really important. It's not for 2. That doesn't show increasing or decreasing. It's for every one of them implies that f of x1 is less than or equal to f of x2. Now, I know this isn't the definition you wanted. I get it. It wasn't the definition I wanted either, okay? But remember, math is proof, and you can't say, oh, function goes up, okay? As you read left to right, function goes up. You can't prove anything with that. That doesn't make, there's nothing mathematical you can prove with that. This is something that we can prove. Function goes up, we can't prove. But graphically, let's just take a look, and I want to show you. The definition is really kind of exactly what we thought it would be. So if I have a function, now I remember my professor, back Professor Folks, who had a PhD in Latin and a PhD in math. He asked, is this function increasing or decreasing? And he drew something that looked like this. And then he goes, is it increasing or decreasing? And then he asked me, is it increasing or decreasing? And I'm like, well, it depends. And he goes, it depends. What do you mean it depends? And I'm like, it depends on which way you're walking. And he's like, what? He looked at me like I was just a moron, because I am dyslexic. Reading is one of my least favorite things, so I don't do much of it. So he was just assuming that everybody understood that we're going to go in the same way we read, that we're going to move from left to right. I'm like, okay, well, it depends. If I'm walking this way, then I'm walking up, and if I'm walking this way, I'm walking down. I don't know. It could be increasing. It looks increasing and decreasing. But when we're talking about increasing and decreasing in mathematics, it is like the way we read. Is as we go from left to right along our domain axis, is our range values, going up or down. And hopefully everybody here would say this function is, and what do you got for me? What do you got for me? Danny man, what do you got for me? What do you say it is? Well, hopefully you said increasing. Okay, so guys, this is like my domain D, okay, in between here. Okay, so if I'm looking at my definition, okay, we all agree this function f looks like it's increasing. Okay? Now, then I should be able to pick any x1 and x2 in D, with the only constraint being that they're in D and that x1's less than x2. And typically, guys, when I'm teaching this, I have my students come up and pick the points, just to show that I'm not like doing a shell game. Okay, so I'm gonna pretend like I'm somebody coming up, and I've come up, and I'm randomly gonna pick 2 points. The only requirements are that they're in D and that x1's less than x2. So I'm just gonna pick, here's an x1, and here's an x2. And we all agree that we understand that this is now an increasing function. Now I want to show you that this meets the definition that we've got there. Because if I look at f of x1, it's here. Well, f of x2 is there. And I don't care where you pick your x1 and x2, anywhere you want, as long as x1 is less than x2, if we're looking at that graph, it's going to meet this definition. Now, I know this is annoying. I apologize. It annoyed me too. In mathematics, we use the word increasing, even though it can be equal to. So you wouldn't think a function that looks like this then dies off and stays steady for a while and then shoots back up. I wouldn't think of that as being increasing. But in mathematics, we call that increasing. I'm not going to hold you accountable for these subtle differences. We call this a strictly increasing. Strictly increasing. Okay? Well, both of them are increasing. So strictly increasing, we just get rid of the equal to, but I'm not even going to like worry about strictly increasing. Okay? Your boss, if you're dealing with money, they may be more concerned about you understanding strictly increasing. And now we can imagine that, and again, hopefully that you have an understanding of that. Decreasing follows the same kind of way. If I've got a function that's like always going down, as we really read left to right, and again, as long as x1's less than x2, this stays the same, this stays the same, but we can see on what we intuitively think of as a decreasing function, then things flip for us over here in the range. In this case, f of x1 is bigger than f of x2. So even though the definition isn't what we wanted, okay, but we got to remember math is proof, and going up ain't going to do it. Okay, this is something we can actually prove. This is something we actually work with. But here's the guys, this definition to actually work with is a pain in the butt. I mean, even for very simple polynomial functions, it is a pain in the butt to show that a function actually is increasing or decreasing using the definition. You take a function as simple as like f of x equals like 7x cubed minus 4x squared plus 5x minus 8. And I say find the intervals of increase and decrease on that using this definition. You're toasted. You're toasted. There's no way it's going to happen. Okay. So even though this is the definition, it's not a real easy definition to use. Okay. And that's where our good buddy, the nice value theorem, is going to come in and really help us. Okay. The mean value theorem is going to come in and save the day. Now, because not all functions are continuous, and not all functions are differentiable. Really important functions are not differentiable, okay? Don't be thinking that every function is continuous or differentiable, okay? Because that's not the case. We do need this definition, okay? We just can't use our calculus. What we're going to end up thinking is the definition, which usually ends up burning kids on a true-false question on a test. But if it is differentiable, boy, it certainly makes life a whole lot easier. Okay, so now what I want you to do is just pause the video. Okay, I'm going to erase the board, scroll ahead, and we're going to prove 2 more results, and then I'm going to let you go. We're going to prove 2 more results, and then I'm going to let you go. All right, so I'm going to erase the board. You pause the video. You don't have to watch me erase the board. I could sing for you while I erase the board. I'm erasing the board. I'm erasing the board. I'm erasing the board. Okay, now, let's talk about this theorem right here. I want to make sure I don't get lazy and write the thing down. Okay. And at first you're going to say, hey, Dr. One, you're writing down the mean value theorem again, but I'm not. Okay, so don't yell at me. Okay, theorem: if f is continuous on the closed interval AB and differentiable on the open interval AB, and you're like, Dr. One, you're lying to me, man. This is the exact same thing that you wrote down. Okay, well this is where it changes, and f prime of x is greater than 0 I guess we did fine with greater than or equal to 0 for every x that's an element of that open interval AB, then f is increasing on that closed interval AB. So this is a really sweet theorem. What we're saying is that, you know, this definition, and normally what I would do, guys, is I would have you sit there for about 10 minutes, okay? But I don't have 10 minutes, Dad. I would have you sit there and for about 10 minutes and try to show me. I'd pick an interval where I actually knew what this function was doing. I just made this one off the top of my head, so I don't know. But I would give a function that I've actually looked at, give you an interval, and say, prove, using this definition, that the function's increasing. And just what you just sweat, look, confused, have kids try to do crazy algebra stuff, and just be dead in the water trying to show it. Where this function comes in and makes life this theorem comes in and makes life a whole lot easier. Okay, so if your function is again closed interval, we want to use the mean value theorem. And if the derivative is positive on an interval, then the function is increasing on the interval. That's the bottom line, okay, from this result. If the derivative is positive on an interval, then the function is increasing on that interval. Okay, so one more time. What did I say? Let's get the result now. Say it again. That's right. Say it again. This is the third time. My dad used to have to spank me 3 times. Okay, remember I stick in the fork in the electric socket. Okay. If the derivative is positive on the interval, then the function is increasing on the interval. But math is proof, so we have to prove this. We have to prove this, okay? And where in the room is the definition? Where in the room is the definition of increasing? Where in the room is the definition of increasing? Okay? And hopefully you're pointing up here, Caleb. Hopefully you're pointing up here. A function f is increasing on a domain D if and only if, for every x1 and x2 that's an element of D, okay, so we got to show that this holds for every x1 and x2 that's an element of D, such that x1's less than x2, we must reach the logical conclusion that f of x1's less than or equal to f of x2. And that's not going to be easy. I mean, if you're thinking about it, that's going to be a bit of a challenge. Okay, so remember, all of the stuff on this side of the implies is given to us. Okay, and then we've got to put together an argument. So we're going to be given a closed interval AB. We're going to be given that it's differentiable on a closed interval AB. We're going to be given that x1 and x2 are somewhere in that closed interval AB, such that x1 is less than x2. So let's just start unpacking our givens. Let's just start unpacking our givens. Okay, so what we're going to say here, this is going to be my justification. I'm going to get lazy, so I'm not going to call it a proof. My justification. So I'm going to just say let, that creative let again, let x1 and x2
the elements of the closed interval AB such that x1 is less than x2, okay?
So we're unpacking what we're given. Okay, now what we need to argue is that then it must logically follow that f of x2 is less than f of x1. Okay, so
Let's just give ourselves a graph here. We've got an A and B, and we're trying to show a function's increasing, so let's assume that it actually is increasing, something like this. We're going to pick an arbitrary x1 and x2. Now remember guys, this could be x1, and that could be x2, so that would be a case we need to consider, you know, but let's just say our x1's here, and our x2's there.
Well, since x1 and x2 are in the interval AB, then it does logically follow that the closed interval x1, x2 is then a subset of the closed interval AB. And you can see it right here. I mean, just in our picture, okay? I mean, we've got our closed interval AB. Well, this closed interval is a subset of this.
And since f is continuous, was given to us to be continuous on the closed interval AB, it is also continuous on the closed interval x1 and x2. And my sentence is getting horribly long, but I think I'm going to still go with it. And since f is differentiable on the open interval AB, it is also differentiable on the open interval x1 and x2. And you say, Dr. One, what are you doing? What are you setting us up for here? Okay, well, I'm just asking, is anything that I'm saying not true? Is anything that I'm saying not true in this justification? Okay, so I'm saying that x1 and x2 are in the closed interval AB. x1 could be A, x2 could be B. Since they're in there, then this closed interval is going to be a subset of the closed interval AB. Every element that's in this interval, we can argue will be in that interval. And since f is continuous on this closed interval, it's going to be continuous on this closed interval, because this is a subset of the other closed interval. Since it's differentiable on the bigger interval, it's going to be differentiable on the smaller interval. Okay, so now this has set us up to use the mean value theorem, but not with the letters that you think. We're not going to be using the A and the B. The ones that we want to use are the x1 and x2, or the x1 and x2. So now I'm running out of space here. I'm running out of space, so I'm going to start working up here, and I'm going to erase what I have. So you guys are going to help me out, because we're essentially going to rewrite the same thing down up here. So my proof is now jumping up to here. Sorry, this is like working with me. Okay, so instead of going down, we're now going to jump up, and then we'll probably have to jump back down. I had to look around for a long time to find a classroom to teach in. So now we're in some
obscure room here. Not really sure. You're actually, again, like the camera's on a chair. I'm still hoping it's gonna stand. But here we go. Since we're continuous on the closed interval x1, x2, we're differentiable on the open interval x1, x2, then by the mean value theorem, there must exist. Now remember, I just erased what the mean value theorem guaranteed. But you are watching a video, so you can actually pause it and scroll back and look at the board. There must exist a what? There must exist a C in the open interval. Now it's not AB, it's x1, x2, such that f prime of C is equal to not f of B minus f of A, but f of x2 minus f of x1, and not over B minus A, but over x2 minus x1. Okay, so again, this is the big thing. We're using the mean value theorem. Okay, we're using the mean value theorem. And again, because we use the word let, it's the creative let. It's any x1 and x2. Just like we were using before, let epsilon be greater than 0. It's any epsilon greater than 0. So we're showing it for all x1 and x2, such that x1 is less than x2. Okay, so now here we go. There's one thing that we were sent into the field with, one weapon that we haven't used yet. Okay, and we're going to use it in really two. One is that x1 is actually less than x2. Okay, so now what I'm going to do, since x1 is less than x2, then this is not 0, which is good because we've got x2 minus x1. Okay, so what I'm going to do is I'm going to multiply both sides by x2 minus x1. So this would imply that f prime of C times x2 minus x1 is equal to f of x2 minus f of x1. So hopefully you guys, I mean, I know it's boring, okay, but hopefully you're not puzzled by this move. All I'm doing is multiplying both sides by x2 minus x1. Now you might be going like, Dr. Warren, why are we doing this again? I forget what this thing's even about. Remember, what we're trying to show is that if the function is continuous on the closed interval and the derivative is positive, then it's increasing. Then the function is increasing. Now where's the definition of increasing again in the room? It's up here. So ultimately what we're trying to reach is that conclusion. Now notice, these two players are now on our soccer field. These two players are now on our soccer field. Okay? And hopefully you're beginning to see where this is going to go. Since x1's less than x2, this implies, I'm not doing anything clever, all I'm doing is subtracting x1 from both sides. This implies 0 is less than x2 minus x1. Now notice when we subtract, we don't flip the sign. It's only when we're multiplying or dividing by a negative that we flip the sign. So I know that x2 minus x1 is greater than 0. But, and I guess I'll go all the way over here, but f prime of x is greater than 0 for every x that's an element of the open interval AB. But the open interval x1 and x2 is a subset of AB. So this implies that f prime of x is greater than 0 for every x that's an element of x1 and x2. But where is C? C is in the interval x1 and x2. So this implies that f prime of C is greater than 0
as f prime of x was given greater than 0 for every point in the interval AB. So now we know that f prime of c is greater than 0, and x2 minus x1 is greater than 0. So f prime of c is greater than 0, and x2 minus x1 is greater than 0. Like for example, this would be 7, this could be 3, and 7 times 3, would that be positive or negative? Okay? What did we prove when we were looking at the real numbers? Remember, we didn't just say a positive times a positive is a positive. We used our properties of the real numbers to justify for the first couple weeks in this class that if a number is greater than 0 and you multiply it times another number that's greater than 0, that in fact that their product is also greater than 0. So since f prime of c is greater than 0 and x2 minus x1 is greater than 0, and by a previous theorem, their product is greater than 0. Okay, but if A is less than B, and B is equal to C, then what's the logical conclusion? If A is less than B, and B is equal to C, what's the logical conclusion? Well, this would imply, and I guess maybe I won't have to go down, this would imply, so I guess I'll squeeze it all the way in over here. Well, I don't know, maybe I'll just finish down here. This would imply then, from what we have up here, it's kind of like a transitive property, with a little bit of symmetric mixed in, that 0 is less than f of x2 minus f of x1, and then we're really close, which implies that f of x1, all I'm doing is taking the f of x1 to the other side. And again, I don't flip the sign. Here, and look guys, we're exactly where we wanted to go. We're exactly where we wanted to, because this includes, this less than or equal to includes this less than or equal to includes this. So if if the derivative is positive on an interval, then we've met the definition. We've argued that the function must be increasing on that interval. We've argued by the use of the nice value theorem that the function must be increasing on that interval. Okay, so you can pause it again. We've got one more result, and then I'm going to let you go. We have one more result, and then I'm going to let you go. Okay, so just pause it again, and then you just scroll ahead. Now, you guys, before I guess maybe I'm not going to erase right now. I just want to show you, like, guys, if the derivative is always negative, you can go through here. Everything's going to be the same. I mean, if you're just looking, everything, you can just look at this result. Everything's going to be the same. Certainly this picture isn't going to be the same. Everything's going to be the same. Everything's going to be the same. We still have the mean value theorem. Everything's going to be the same. x1 still given less than x2, so this would still be a positive number. This would still be a positive number, but in this case, the derivative would be, if the derivative is negative, then my f prime of c would be negative, and then we would have a negative times a positive, which again, we proved would be a negative. So we'd be able to argue that this would in fact be less than 0, which would give us the flip around that we would need to show decreasing. So guys, the proof is identical for showing decreasing. The proof is identical for showing decreasing. Okay, so, and oftentimes what I'll do on that third test is I'll ask you to show decreasing even though I've shown increasing. Now again, later on, if you haven't picked up on this with teachers, when teachers say something like that, your alarm bell needs to go off. Your alarm bell needs to go off. So I'm going to say it one more time, okay? Oftentimes I will ask my students to prove decreasing even though I've showed them increasing. Okay, so I'm not going to show you decreasing. Okay, so now you can pause and then move ahead. and I won't sing. All right, guys, all right, just pause the video and just scribe what I just wrote down, just scribe. Then after you're done writing it down, then come back and unpause the video. Okay, so now that you've scribed this down, I know you're getting tired, I'm getting tired. Let's go ahead and then just look at what we have here. This theorem says if f is continuous on the closed interval AB, you know, Dr. Moore, you're killing us with this. They're keeping writing the same thing down over and over. And differentiable on the open interval AB, now in this case, if the derivative is equal to 0, not just at one point, some arbitrary point, for every point that's in AB, then the function's got to be a constant on the closed interval AB. And this is just different enough. That I'll actually give a quick justification of this one also. It looks exactly the same. It looks exactly the same. Or very similar. Okay, let x1 and x2 be arbitrary points that are in the closed interval AB. Okay, so they're just any arbitrary points. Okay, so I'll go up here. I've got an A and a B, and I am just picking an x1 and x2. Now I'm not putting any qualifications at all on x1 and x2 here, except for the fact that they're just in that closed interval AB. X1 may be bigger than x2, x2 may be bigger than x1. Now I'm not arguing all three of these cases, or x1 might be equal to x2. I'll argue two of them. I'll let you guys argue the other one for me later on. So this is going to be my justification. Again, this is the creative let x1 and x2 be any arbitrary points in the closed interval AB. Okay, case one. Now, I always used to hate the word case because in a justification because I knew there would be at least two, but in this case there will be three. Case one is suppose x1 is equal to x2. Remember guys, we had trichotomy. Trichotomy says that if you got two real numbers, okay, they're either A is less than B, A is greater than B, it's called trichotomy, okay, or A is equal to B. We're just going to look at this. Suppose x1's equal to x2, okay, well this implies then f of x1's equal to f of x2, okay, and this fell really quickly. What we want to do is argue that f of x1's got to be equal to f of x2. Because if for every x1 and x2 in the closed interval AB, f of x1 is equal to f of x2, if for every x1 and x2 in the domain, A and B, f of x1 is equal to f of x2, then f of x is a constant, and f of x is a constant. So that's ultimately what we're trying to show. Now notice, this one falls pretty quick. If x1 is equal to x2, then f of x1 is equal to f of x2. And this is just by the definition of a function. What's the definition of a function again?
What's the definition of a function? James, what's the definition of a function? It's a relation that assigns to every element in one set called the domain a unique one and only one element in another set called the range. And so where x1 is equal to x2, that's the same domain value. You can't have it being sent to two different range values. So this one we have that that f of x1's got to be equal to f of x2 just by the definition of a function. So that case was pretty simple. Case 2, suppose, now I'll just do one. We had x1 less than x2, so I'll let you guys do that one. Suppose x2's less than x1. Well, this implies that x1 minus x2 is greater than 0. This implies that x1 minus x2 is greater than 0, or, well, I guess I don't even need that. This implies x1, this is the thing I don't need, this is the thing I can't have. This implies x1 is not equal to x2, and this is by trichotomy. I'm not going to make it any harder than that. This implies that x1 is not equal to x2 by trichotomy. Okay. Since x2 and x1 are elements of the closed interval AB, then the closed interval x2, now notice x2 is less than x1, is a subset of the closed interval AB. And here goes my big nasty long sentence again, I'm not even going to make any better. And since f is continuous on the closed interval AB, it is also continuous, this is pretty wordy, you don't need to be this wordy, also continuous on the closed interval x2 to x1, and since it is differentiable on the open interval AB, it is also differentiable on the open interval x2 to x1. Okay, now I'm going to get excited because I know I haven't thrown much energy at you. My wife's in the room and I don't want to like blow her ears out. But guys, I mean, come on, what theorem are we set up to use? Come on, guys, I mean, seriously, what theorem are we now incredibly, so nicely set up to use? We've got that it's continuous on the closed interval x2 to x1. It's differentiable on the open interval x2 to x1. Then by the come on guys, by the you're not helping me out here, by the mean value theorem, the nice value theorem. I've gotten some shock here in the way. There must exist by the mean value theorem, there must exist a C. Now guys, this is not, again, between A and B. We're worried about x2 and x1. In the open interval x2 to x1, and let me just say, that's a subset of the open interval AB. There must exist a C in this open interval such that f prime of C is equal to f of B, but it's not f of B, it's f of
x1 minus f of x2, because if I'm looking at where my x2 and x1 are, over x1 minus x2. So I'm just using, guys, I'm just exploiting, beating the crap out of the mean value theorem, using it over and over again. Now notice the conclusion we want to reach is that f of x1's got to be equal to f of x2, just like in case 1. But we're really, really good. We know that x1's not equal to x2, so we can't have any problems with the denominator. The denominator is not 0. Okay, so I know the denominator is not 0, but what was I given? I was given that the derivative is always equal to 0 for every x in the open interval AB. But C is in the open interval AB because it's in between x2 and x1. Since C is an element of the open interval AB, this implies, by my given, that f prime of C is equal to 0. And then just substituting that in over here, which implies that 0 is equal to f of x1 minus f of x2 all over x1 minus x2. But we've got this over this equals 0. This guy's ain't 0. So what does that numerator have to be, guys? What does the numerator have to be? And you can also think of it this way. Since this isn't 0, we can multiply both sides by x1 minus x2. I just don't have enough room over here. We can multiply both sides by x1 minus x2. And what did we prove any real number times 0 is? What did we prove any real number times 0 is? And we proved that was 0. So multiplying both sides by x1 minus x2, we get a 0. And so f of x1 minus f of x2 would have to be equal to that 0, which would imply that f of x1's equal to f of x2, which is what we wanted to reach. Okay, so that you give me any arbitrary points x1 and x2. If they're equal, f of x1 equals f of x2. If x2 is less than x1, then f of x2 is equal to f of x1. And you guys are going to take out care of the other case. It's identical to this. It's identical to this when x1, the other part of our trichotomy, when x1 is less than x2, and we'll end up with f of x1 is equal to f of x2. So f of x1 is always equal to f of x2, which means the function is always constant on the closed interval AB. Okay, so this is a really important theorem. This is a really important theorem. It basically comes in these three flavors. The derivative is positive on an interval, it's increasing. It means the function's increasing. We can completely ignore then the definition of increasing. If the function's derivative is negative on an interval, then it's decreasing. Again, we can completely ignore the definition of decreasing. And if the derivative is 0 for every point on the interval, it's important, every point, then the function is a constant on that interval. Then the function is a constant on that interval. All right, guys, I'm sorry for the yellow chalk, sorry for this chalkboard. This room isn't quite as fancy as the other one we found here at Vanderbilt. Again, apologize, I will see you on Wednesday. I hope you have a great day. Again, there won't be any, I'll be on the road tomorrow, so there won't be any Zoom tomorrow. All right, thanks guys, appreciate you. I will see you very, very soon.